So thank you for coming to my mini course. This is my first time to attend the SIMIODE conference. And I really want to thank Brian for inviting me. We were at the joint meeting conference in January, and he extended the invitation to speak here. So it's very good. Yeah, I enjoyed the first talk already. Uh, so let me tell you a little bit about delay differential equations. So this is a topic that I was involved, I think, 4 years ago with one of my students. He asked me, he wanted to work with me. And since I was exploring some topics on functional differential equations, so I'm like, okay, so let's try to look at some application in epidemiology. So this is how I started with the talk, what I'm presenting right now. So I will start with a quote from a French humorist, Pierre Dac. He said, I will say it in French, qu'est-ce que le passé sinon du présent qui est en retard? Let me translate in English. What is the past if not the present, which is late? Okay, so let's see how late is sometimes important. Okay, so I will start with what we know in our differential equation class. We try to motivate students about the differential equation by giving them first application. The first one is what we usually do is the Malthus model. So suppose that you have a scientist, he's studying the growth of a population, and he may make some very simple assumption that the population grows at a rate directly proportional to its size. Okay, so we have what we usually call the Malthus model here. And always we try to motivate the students, say, okay, you already took calculus 1 and 2, so can you tell me what is the function that will give you that the rate of change is proportional to the function itself? And this one student can guess in differential equation class the first day. They can just guess that it's an exponential. And you can have a family of exponential functions, so decay or the growth one. So you can now ask about, okay, how can you specify just one solution? So by imposing an initial condition. And so you can see that we get a solution, an exponential solution here, but we determine a specific solution by only determine one specific time, then you can predict the future. Okay, so we get the exponential one. But the thing is that for a population, this is unrealistic. So this is how we motivate now the logistic equation. So because it's unrealistic that the population can just grow, because we have to take into account the crowding effect. And so we can see that we can modify this problem by introducing the logistic equation. So in 1838, the Belgian mathematician Per Voros introduced the model where now we have to take into account the self-limitation. Okay, so we have what we call the logistic equation. And so the way he modified the Malthus equation is by assuming that per capita growth rate decreases linearly as a function of the population. And so what we have here, the capital R sub P, so we have this growth rate here will decrease. So we have that it's a linear function, but it decays. So we have R times 1 minus P over K. So we have we have the intrinsic growth rate, and we have the carrying capacity. Okay, so what we can see here that the logistic equation assumes that population density negatively affects the per capita growth rate according to this, due to the degradation of the environment. Okay, and now, so if you, as mathematicians, we try to get more realistic. When we do the modeling, we try to simplify the model, but more closer to reality. And so so what we have here for the logistic, we know how to solve that. That we get we use separation of variables, we get a solution, and with the carrying capacity, we know that we will have self-limitation. But we can ask ourselves, so if you look at the problem we have here is that we determine the rate of change depend on the population, but we can say that it depends of the population, but this population is just when we look at the initial time, then you can determine what is, so at a specific time, you can determine the future, the behavior of the function itself. Okay, but now in 1948, George Aitchison pointed out that the negative effects that high population densities have on the environment influence birth rate at a later time. So due to, let's say, maturity delays. Okay, so now he proposed the following problem, where now he modified the logistic equation. Instead of looking at the growth rate here, R sub P, he incorporated the delay, because you have to take into account the past. And the previous two examples we have, so the past is not involved. And so he introduced the delay into the growth rate. And so we have the equation, we have two here that sometimes is called the logistic delay differential equations. Now, there are other examples of delay equations, but I want just to give you a flavor of one that I worked with my student a couple years ago, my former student, because now he's a first-year PhD at Ohio State University. So we looked at the spread of vector-borne diseases using the delay. So where do we have the delay comes from? So suppose that you have, so this is a picture of a transmission cycle of the Zika virus. So you have a susceptible mosquito, which is what we call in epidemiology a vector. And so he's susceptible, but he bites a infected person. And so he's infected, but to become infectious, the mosquito, it takes at least 10 to 12 days for the Zika virus to incubate, and the mosquito will become infectious. Then once he bites a susceptible person, then the susceptible person, it will take about 8 to 12 days for the person to become infectious. So the 8 to 12 days here, we have what you call the incubation periods, when the disease is developing, but you don't have yet the symptoms. And so this is where now, if you want to model the, for example, just for the infectious, how the human population can be infected, so the spread of the disease for the human population, then you have to take into account this incubation period. So these incubation periods are now your delay time, okay? But later on, I will show you just maybe quickly how we did the model. But this is the goal, that every time sometimes I feel like the delay, when you incorporate the delay, you get a more realistic model. But the tricky part about the delay, that is not easy to solve, because you have to be, I can say, mathematically mature to do it, because it involves complex analysis, real analysis. So this is why I noticed that we don't usually teach delay differential equation in our DE class. But what I do every time when I teach a differential equation class, I always give some project on that, so that the student can see the relevant, why it is important to have a model, to think about the delay model. Okay, so let me just give you a simple definition. So the delay differential equation is a differential equation in which you have that the current rate of change of the system depend not only on the current state, but also on the history of the system. Okay, so let's just look at this simple example. So I will focus on this simple example where you can see how much complex is the delay differential equation. But with this simple example, we are at least able to solve the equation 3 here, and also look at the stability of the equilibrium. Okay, so let's look at this simple linear delay equation. So you have that the rate of change depends on the past time. So we have tau here is the delay or the time lag. Now, if you observe in the ordinary differential equation, for a first order, we just need an initial condition at least at one point. But for the delay, because we have this time lag, we need to impose conditions. It will no longer be at a single point, but it will be on an interval. So you have to impose a condition. So you should have an initial function. So this is what is given here. Now, what is interesting about the delay differential equation is that even if with this simple example, you can get some oscillatory motion behavior. Compared to the first order, we know that if you have y prime equals to minus ay of t, we know that we will have an exponential growth or an exponential decay. But we don't have oscillatory behavior. But very surprising, for a simple example like this one, you can get the oscillatory behavior depending on the coefficient A and the delay time tau. Okay, so this is what we have here. So what my student made a map where you can see that we can have oscillatory behavior even if for this simple example. So if I just move, you can see that we are having some oscillatory behavior just for this simple equation that cannot happen in the case of the Malthus one, because Malthus we only have the exponential decay or growth. Okay, so so this was very interesting for my student to see that for a simple one like this, you can have complicated motion. So, and now let me walk through with you how you can end up with oscillatory behavior for a solution. Okay, so now let's make some transformation here. So I will make the change of variables. So I will call u of t will be y. We multiply y of tau t, and so we end up with the equation 4 here, where now I can say the delay time we just normalize by 1. We make this transformation so that we can have just the delay time to be 1, and beta is the product of the delay tau and the coefficient A. And this beta usually is called the feedback. Okay, so we can have, with the feedback beta here, you can have some oscillatory behavior or non-oscillatory behavior. Okay, and so by looking at the problem 4, so the differential equation, the equation here, so you can see that we have only one equilibrium. So we have that is u at 0, so where the solution does not depend on time t. Now, if we have to look for another solution, and because of the form of our differential equation, so we know we look for a solution of type exponential. So like we do when we teach second order differential equation. So what we have now that plugging it into the equation, we have instead of having an algebraic equation, we get a transcendental equation. So if we are able to solve and understand the root of this transcendental equation, it will be very helpful for us to study the stability and also the oscillatory behavior of the solution. But this is where now complex analysis is involved, because we no longer have the algebraic equation that we used to have for the characteristic equation that we always teach, but now we have a transcendental. We don't know how many number of solutions that we can have here. And so we have to study this transcendental equation in order to have more information, for example, of the stability of the equilibrium and also the behavior of the solution here. Now, if you look at equation 5 here, the characteristic equation, I can rewrite it as lambda. So lambda equals to minus beta e to the lambda, e to the minus lambda. And so I can look at the number of solutions by looking at the equation here. So first I will look at, because lambda can be a real number or a complex one. So if you look at if lambda is real, so let's assume that lambda is real. If beta is negative, so you have, if beta is negative, you can see that the equation lambda equals to minus beta e to the lambda, you will have that lambda will be always greater than 0. It will be positive. And so we have that the equation, the line, I can say G equals lambda, and the curve, the exponential one. So you have that the intersection will be at a single point here. And the intersection is on the positive part of lambda. And so the solution, the non-trivial solution, the time-dependent solution will be, we know that we will have lambda sub 0, a positive real root. And so you can see that lambda sub 0 is positive. Therefore, our solution returns to infinity as the time goes by. So our equilibrium will be unstable. Okay? And now, if beta is positive in this case, then our function now, it will, the minus beta e to the minus lambda one will be the blue one I have here. And then we have the line G equals to lambda. And so you can see that if beta is between 0 and 1 over e, you have that the intersection of, the line and the curve at 2 points. And these 2 points are on the negative part of lambda. And so what we have, that because our solution is of exponential type, so because the 2 lambdas are negative, so they will tend to 0 as t tends to infinity. So what you have here, that our equilibrium will be asymptotically stable. And then when beta reach e to the negative 1, so the intersection now will be, so we have that the e to the negative 1 is the tangency point. So we only have the intersection with the curve and the line at 1 point here. And so what we have here is that lambda will be -1. And so what we have is that still our U star 0 equilibrium will be still stable. But when you pass the point e to the -1, then what we have that the curve and the line, they do no longer intersect. And so we have no real roots, okay? And now, but we can have other solutions that can be complex. And now when lambda is complex, in this case, we can rewrite our characteristic equation. So we have the real part, we can express the real part and the imaginary part here. And and then I can rewrite the real part in terms of the imaginary part. I can divide by y because I know that I'm considering a complex one, so y is not 0. Okay, so the imaginary part is not 0. Okay, so I can divide by y. And so now what I get a parametric equation. So I have the real part, and I can also express the feedback parts here, beta, by this. And you can plot that. So the dotted one are when you only have lambda is real, and then the solid curves are when you have that lambda is complex. Now, what we observe here is that to study the root here, you just need to look at the leading root, and the leading root is when you have that. So the real part is greater than all the other real part of lambda. And so what we have here, so I just with this picture, so the leading root will be what I have, the top one that I have, and then the dotted one is what I said that is for the real root. Okay, so lambda real. And now by looking at this, we have that if beta is negative, so we have the plane here, we have the x-axis is beta and the y-axis is the real part of the of our eigenvalue lambda. And so when you look at when you have beta, if beta is negative, we have that the curves here, there is only one leading real root that is positive. So we can see that we are in the, look at the dotted one. And so U star in this case is unstable, okay, because we can write our solution as an exponential one. And now, so when beta is between 0 and e to the negative 1 is what the blue dot that I have here is what we have, that is e to the negative 1. And so we have that the leading real root, they are kind of negative. And so U star, our solution, our equilibrium will still be asymptotically stable. But now between e to the negative 1 and pi over 2, we observe that what we have here is still, we have that still negative. And so what we get here is that still we have negative, and so the equilibrium is still asymptotically stable. But when you reach pi over 2 is the intersection we have in blue, the intersection with the x-axis, the beta axis here. And so we see that we get that the zero solution in this case will be unstable. And then for beta greater than pi over 2, you get that you have that the leading coefficient here is still greater, is now positive, and so we get that we have again the zero solution will be unstable. And so what we observe that is that the zero solution is asymptotically stable only when beta, the feedback, is between 0 and pi over 2. But how do we, why do we have the oscillatory behavior? So what we observe is that if you take beta small positive, the solution will decay exponentially towards 0. But when you just hit value around e to the negative 1, the solution becomes oscillatory, okay? And it will still decay to 0. And when beta hits the number, I can say pi over 2, then our oscillatory will become, it will, we will have an oscillatory, but now the amplitude will keep growing. Okay, so this is what we have. And you can show that every solution of the D is oscillatory when beta is bigger than e to the negative 1. It's always the case. Okay, so let me show you with the, I lost it, so let me see. So what I just talked about here. So when I say simple DD with positive feedback, so that means beta is negative. And if you look at, we always have exponential one. So we don't have any oscillatory. So when the feedback is positive, you can see that because we have u prime equals minus beta u. So when u and beta and u prime will have the same sign all the time. And so, but when you have that beta is negative, this is where now we have the oscillatory behavior. So we always have, so it's kind of different. So we can have this. But you need to study to look at the eigenvalues of the transcendental equation. This is where now it's a little bit tricky to study, but it's with the simple example, it's possible. And I don't know how many minutes I have.
You have 5 more minutes.
Okay. Yeah, so this is what I mentioned to you here. And so, but when you have beta is kind of pi over 2, there is no decay. It's just the oscillation is kind of, the amplitude is not changing. But when beta is like beyond pi over 2, so you have the oscillation, but it's kind of now the amplitude is increasing. Okay. And so we apply, we wanted to see how we can use that for the vector-borne disease, as I mentioned to you about the graph of the, so the transmission cycle of the Zika. So what we did, we look at the problem, we use the compartment model here. And so you have S is the susceptible one, and then you have the exposed and the infected person, and Z is the mosquito one. And so, like I said, we were interested in the dynamics of the infected human. And so we make several assumptions. So the first one is when you get you get infected and you become infectious, but we assume that the population is fixed. Is capital N, and then we include the incubation for human and the incubation for the vector one, and also we assume that the infected vector population is proportional to the infected human because of the number, and so we get this model here. But if you look at with the assumption, we will get the model 8 here, but when if you look at the equilibrium, you have two, the disease-free and the endemic one. When you do the linearization around the equilibria, what we get is similar to what we just studied in the case of a simple DE. And so you can use what you do for the simple case to study the stability of the disease-free equilibrium and the endemic one. And we observe so many behavior here, but what was easy is because we got a better understanding of the simple case, and it was just a matter of making the transformation to get the answer for the stability for the disease-free and for the endemic one. Okay, so this was a work that I did with my student, but I had this student since his freshman year, and he took several classes with me. So when we started this research, he was like a sophomore, rising sophomore, but we were able to look at, but he has to read a lot so that he can come up with the conclusion with the result that we published last year. Okay, so I think I'm done, and thank you.
All right, and that's the phone ringing in my house. So one thing about being in the middle of your house. Anyway, thank you very much. We can all give our claps. And again, if you want to quickly turn on your video, so doesn't feel so much like people are teaching to an empty classroom. But thank you very much. And maybe you can put your email address in the chat. Again, make sure you do it to everyone, so then that way people can email you if they would like a copy of your presentation, which I believe will be eventually available, but I know I like to get things right away before I forget about them. So any questions? Is your student still at school, or did he or she graduate already?
He graduated last year, so he's a first year now, a graduate student at Ohio State. Yeah.
Oh, excellent, excellent. Wonderful. And what is he studying at Ohio State?
Yeah, he's doing applied math too. So he I think he's maybe because of what the work he did here that he just want to continue doing applied math.
Excellent.
I have a question.
Yes.
Can you give an intuitive reason why you get the oscillatory behavior? I mean, I can, follow the math, but is there like an intuitive reason why you would get the oscillatory behavior with delay?
Yeah, so let me, it's maybe I can explain it from this the equation here. Okay, so if you have that the beta is negative, beta is positive, this is where we have the oscillatory behavior with that. So it's more with beta is negative. So U prime here will be, if for example, you start with U negative, the initial condition, the initial function, let's just take the initial function to be a constant one, is negative, then you have that the right-hand part of 4 will be, it will be positive. So it will keep increasing. Okay, so the function U of t at later time will be greater than the one that you started with. And so at some point, you will reach U positive. And then when U is positive, so that means the path becomes positive, that means U prime is negative, you will keep decreasing. And you will keep decreasing until you reach a negative value. And then U prime now becomes positive, then you have to go up. So this is why we get this oscillatory behavior.
Okay, thank you very much.
Dr. Mavinga, I have not seen yet your email. I would love to email you. Thank you.
Yeah, you're welcome.
So yeah, when you're screen sharing in Zoom, it's not always easy to see the chat. And again, make sure you click on everyone. There we go. Perfect.
Thank you very much.
Yeah,
Thank you.